But
Can I ask you a silly question?
Sure, of course.
If the Higgs is composite,
Yes.
Do you believe the graviton then is also composite or is fundamental?
It's neither. It doesn't exist.
Man, talk about fighting words.
Yes. Going back to this conformal theory, when you quantize it, you find something very, very strange. And that is, it's a fourth order theory. So you would say, I'm going to have two gravitons because I've doubled the number of degrees of freedom. But there's a theorem due to Weinberg which says that if you have a spin 2 particle, it must couple through the Einstein tensor. And therefore, I can't have that occur. But there's an escape clause. And the escape clause is it requires that the metric of that Hilbert space be positive definite. Now, we said a moment ago, but I just showed you it wasn't negative definite. But what I didn't tell you, because it was unrelated at the time, it turns out that I get zero norm. And so what happens is the graviton becomes a zero norm state, not a positive norm state. And so you have gravitational radiation, because it's a covariant metric theory. But when you quantize the gravitational radiation, you don't get a particle. Even though we always did that with photons, because that presupposed that you had a Hilbert space of positive definite norm. And Carl and I wrote a paper to show that in these fourth order theories, you can actually get zero norm gravitons. And so the result of that is that they're not observable. Now, I'm going to say something which you should never quote me on. Well, I've written it, so I'll say it. It's possible that the collapse of the wave function is due to the emission of the zero norm gravitons that we don't observe.
I subscribe to The Economist. Their science and their AI coverage is among the best I've found anywhere. And I say that as someone who reads plenty of it. I'll give you some examples. They just ran an analysis on how attitudes towards science are changing in American politics and what this means for research and funding in scientific institutions moving forward. This sort of high-quality reporting is fantastic. They even covered how dark energy may be weakening over time. Now, if that holds up, it completely changes our understanding of the universe's fate. If you watch this channel, those are exactly the kinds of questions that we explore every week. I subscribe to The Economist because their science and their AI reporting regularly surprises me with how deep it goes. And they're also, of course, known for global affairs, both political and economic reporting. They are top tier, and interestingly and flatteringly, TOE is one of the only podcasts that The Economist partners with. So as a listener, you get an exclusive 35% off. That's not a deal that they have just anywhere. Head to economist.com/TOE to subscribe. That's economist.com/TOE for 35% off.
But that's about as far as I've gone on that question.
This is interesting. I'm going to get you to go a tad further.
Yes.
Because there are two other theorizers that I see you be extremely close to. One is Turok/Latham Boyle, which I'm going to just place as one theorizer.
Yes.
And then the other is Roger Penrose.
Yes.
So taking the symmetries of a light cone extremely seriously also reminds me of twister theory, and then the love for conformal symmetry and his conformal cyclic cosmology it also has a rhyme there.
Yes.
Now you saying that gravity may be connected to collapse also has a rhyme with Roger.
Yes, of course.
And there's so many other rhymes with Turok, Boyle, and that whole research program as well. So I'm wondering, what is the relationship between these two broader research programs?
I have visited Neil and Latham in Edinburgh a few summers ago, and what they're doing is they have a CPT invariant universe, which has the universe that we have, and then there's a mirror reflection of it, and that can get rid of the Big Bang singularity, and that's exactly what Roger Penrose is doing as well, because he has a cyclic universe. And when I first started working on conformal gravity, I realized that it had a cyclic solution, you see. And that would have been the case if the curvature were positive. But when I finally showed that the curvature was negative, it's a theory which never has a singularity. And the way the theory solves the flatness problem is by never being singular. And so, I mean, roughly the following. You write down a dot squared plus k is equal to rho, is the Friedman equation. Rho goes like 1 over a to the 4. 1 over a to the 4 blows up when a is 0. A dot blows up when a is 0, and k is irrelevant. And that's the flatness problem. So to get round that, Alan Guth has an exponential growth before then. But what I do is I say, yes, but you've got the wrong equation. It's a dot squared plus k is equal to minus rho. And then there's no singularity. And so then you've got one universe that lives forever with no Big Bang. And that means that in the early universe, the radius is finite. So that's a little bit different from what Penrose and Turok and Latham Boyle are doing.
So there's no period of inflation?
No, because you never needed it. Because the universe, if you look at the integral of dt over a of t, and you take a of t as t to the n, if n is less than 1, then the integral of dt over t to the half is t to the half, is finite. And that's the horizon. If you do dt over t, you get log t, which blows up at t equals 0. If you do dt over e to the ht, it also blows up. It also has no horizon. So you will get a horizon for any theory for which the expansion radius is t to a power greater or equal to 1, and exponential is certainly in that category. So you don't need to be exponential to solve the horizon problem, and you don't need inflation to solve the flatness problem. Now, I said before that inflation in the end doesn't solve the flatness problem, because what it shows is that omega m plus omega k plus omega lambda is 1, that omega k is suppressed by this exponential expansion in the early universe, so you get that omega m plus omega lambda is 1. Fine. However, before you had lambda, you had omega m equals 1, and therefore you had a prediction that the matter density of the universe was critical. A critical density meaning it equal to 1. But when you have omega m plus omega lambda equals 1, you've now got a real problem, because omega m is redshifting, omega lambda is not, and they have to add up to 1 today. So that's the 0.3 and the 0.7. So somebody had to adjust the very early universe 10 billion years ago such that the matter density would fall in such a way that it would just be catching up with, that lambda would just catch up with it today. So you've still got a fine-tuning problem, which is called the cosmic coincidence problem. But inflation was introduced to get rid of fine-tuning. And yet you still have a new, you've solved the fine-tuning,
right, yes.
Now you've got a new one. So what was thought when the accelerating universe was first observed, which was 28 years ago, it was thought that something would happen before inflation, which would be related to quantum gravity, that would lock you into those values so that it would take 10 billion years before omega lambda could build up to 1. And so people looked to string theory to see if they could solve that problem. Can you show that there's a string theory, very early universe, pre-inflation, which will lock you into the right values of omega m and omega lambda? Now, of course, that hasn't happened. People always say that string theory can't be falsified at ordinary energies. You have to go to Planck scale energies. But that's not true. We know that omega lambda is 0.7. We know it's not 10 to the 120. Therefore, string theory has to explain why it's 0.7. Otherwise, it's falsified. If string theory could come up with a number for omega lambda and it turned out not to be 0.7, then string theory is falsified. And that's at ordinary energies. So that's the challenge for string theory, is to explain why it's not 10 to the 120. And for the moment, it looks like the more natural thing to occur in string theory is anti-de Sitter, not de Sitter, which would make a mega lambda negative. Now, that's not the only thing that can happen, but overwhelmingly it looks like you get a mega lambda negative. And so that problem is still there. There's still a fine-tuning problem in inflation, even without string theory. And despite everything, omega m equals 0.3, omega lambda equals 0.7 really works remarkably well for the fluctuations. And so if I'm going to be able to get anywhere, I've got to recover those results. Otherwise, I have a theory of nothing, not a theory of everything. Even with everything else I've done, with the dark energy, with the dark matter, with the quantum gravity, with the PT theory, with all of that, I still have this problem of I still have to solve the fluctuation. It's not that I can't. It's not that I've calculated them and it didn't work. I just have this problem that I have to do the calculation, and that's where I am at the moment.